Okay, we have seen in the first video the Laurent transformation and its consequence on the addition of velocities. So when we go from one reference frame to another reference frame. Now, let's see what the consequences on the time duration and the length. So the Laurent transformation applied to if we want to measure in a period in two reference frames or a length of an object in two reference frames that are moving with respect to each other, there is a difference because now time is not absolute and length also is also relative, so it's not absolute. So let's again take a very small drawing. This is k prime, which is x prime, y prime, z prime, a reference frame, and another reference frame, x, y, and z, k. And let's assume that we have an event that is here, something like an event that is measured inside this reference frame that is moving, let's say a space shuttle, and inside the space shuttle there is a light flash that is being measured by someone inside the reference, inside the space shuttle. So we have here two reference frames that are moving with respect to each other. So for the same event, one of them will measure, one observer will measure a time that we call t0, and the other will measure time t. And the time dilation equation becomes time dilation becomes the time measured by one reference frame or by an observer in a reference frame is equal to time measured by the other one divided by 1 minus v over c squared. Okay, this is v. Okay, c is the speed of light, v is the relative velocity. Now here we go to the concept of the proper time. In fact, since the time is not absolute, there are two different times now. Which time is the proper time? And I will define or explain what is proper time, but we can also simplify this equation as gamma t0, because gamma, remember, gamma is 1 over 1 minus beta squared, and beta is v over c. Okay, so what is the proper time? The proper time, we have explained this in a course, and there are plenty of material that explain what is the proper time. The proper time, which in this equation, it is the one which is called t0. The proper time is the time difference. So the proper time is the time difference measured between two events that occur at the same position. For example, as I mentioned, a flashlight or a movie that is being projected in a space shuttle, for example, in a system, and as measured by a clock that is at rest in that system. Okay, this is the proper time. So if you have two space shuttle, if you have a space shuttle that is moving away from the Earth, for example, and inside the space shuttle someone is watching a movie, for example, this movie would have, for example, 20-minute duration. So this is the proper time, and someone on Earth will try to measure the duration of that same movie that is moving, of course, inside the space with the space shuttle. So that observer on Earth will measure another time that is t, that is different than 20 minutes, that is larger than the 20 minutes, just because its time got dilated. Okay, so this is the time dilation equation. There is also another consequence on the length as well. The same thing if we have an observer on, let's say, to simplify it, on Earth, X, Y, Z, and there is a space shuttle that is moving with a velocity v, so reference frame k prime. And for example, if I have an object here and this object, I have the length L0. Again, the length contraction equation, we will not measure the same time, the same length, and the length contraction equation that relate the length measure for the same object by an observer on Earth and the length measured by the same object for the same object by an observer in space shuttle, this length contraction is equal to L0 1 minus beta square. Of course, beta is equal to V over C, or we can also write it as gamma, and gamma is 1 over 1 minus beta square. Yeah, so the proper length is the length measured at rest. So, for example, as I mentioned, we have an object that we are trying to measure, and this object is located in a space shuttle, and it is at rest in the space shuttle, and we are measuring it. So we will be measuring the proper length. Someone who is watching the space shuttle moving will measure another length, which is smaller than the proper length. So the proper length L0 is the proper length. So this is very, very important, or those are the two very important consequences of the special relativity and the Lorentz transformation that is that we got from the special relativity. Let's give an example. This example is the following. The lifetime of a pi meson in its own reference frame is 26 nanoseconds. Now, remember, in particle physics and high energy physics, we deal with particles, and we deal with the very, very high speed particles. That's why the time is completely different. The special relativity is fully applied in high energy physics, because we are talking about very, very high speed particles. And also we are talking about small lifetime particles. So this particle has a reference frame that is a lifetime that is measured on its own reference frame. Now, there is one remark here. The lifetime of a particle, any particle that you find in books or in data booklet, it's always measured on the reference frame of the particle, which means when the particle is at rest, it is always measured on its reference frame, which means that the lifetime in this case is the proper length. Okay, so the proper time is 26 10 to the negative 9 second. This is because the lifetime as given here is measured on the reference frame of the particle, and that's why it is the proper length. So the question is, what is the lifetime measured by an observer on Earth if the pi meson moves with speed of 0.95 c with respect to the Earth? So, for example, I have the Earth here, the reference system, which is the Earth. Okay, and I have the particle that is moving with a velocity 0.95 c. Okay, and this particle has a lifetime t0. So what will be the lifetime measured by an observer on Earth? Well, this is very straightforward, because the observer will measure an relative time that is not the proper time, because the particle is moving with respect to each reference system, to his or her reference system. So what we have to do is to apply directly this equation, which is t0 divided by 1 minus beta squared. So we know that v is equal to 0.95 c, c is the speed of light, which means beta is equal to 0.95. Okay, so then the time measured will be 26 10 to the negative 9 second divided by 1 minus 0.95 squared, which is equal to 83.3 10 to the negative 9 second. Now you can easily see that the time measured by an observer on Earth or on the laboratory is larger than the actual lifetime that the particle measured in its own reference frame. So the second question, which is interesting, what is the average distance this particle would travel before decaying as measured by an observer at rest on Earth? Let me explain this. So this particle, the particle, let's say it has been created at this moment, okay? And this particle will live a lifetime. It will live for a certain period. So it will travel a certain distance with a certain speed, and then it will decay. So that's why we call the lifetime of the particle. After the lifetime, it will decay. Okay, so because the particle has a constant speed, it's obvious that the distance is equal to the speed times time. Now, we want to measure the distance. We know that the speed is 0.95 c. But what distance what time we should measure? Well, actually, the time that we should take is the time measured by the guy sitting on the laboratory, because we are talking about the distance in the laboratory, the speed with respect to the laboratory. So we need to take the time that was measured by the laboratory, not the lifetime that is measured in the reference frame of the particle. So this is very interesting. All the quantities should be measured with respect to the same reference frame. So the velocity is 0.95 c with respect to the reference frame k. The time is the one that we just calculated, 10 to the negative 9, but this is the reference, this is the time measured with respect to the reference system, the Earth, the laboratory, and we want the distance measured by the laboratory, by the observer in the laboratory. So D will be 0.95 times the speed of light, 310 to the power of 8, time 83.310 to the negative 9. And the distance, of course, will be in meters, which will be 23.74 meters. So this is a direct consequence of the time dilation equation. Okay, let's go to another example. This example is also very interesting. Here we have two events that are occurring in inertial reference frame K. Okay. So one event has this coordinate. One event has this coordinate, and the other one has this coordinate. You can see that the two events are not occurring at the same time. So the event number 1 is occurring at time 2a over c, and event 2 is occurring at time 3a over 2c. The question is, in what reference frame, K prime, these two events will appear to occur at the same time, okay, will appear to be simultaneously. Okay, so all what we have to do is to say, okay, those events, let's assume those events, this is a reference frame K, okay, and those events, they have, I can, So the event has x1, y1, z1, t1, and x2, y2, z2, t2. So both of them are in a reference frame K, are measured in a reference frame K. Now let's assume that there is a reference frame K prime. There is a reference frame K prime that is moving with respect to a reference frame K with velocity v, and in which this reference frame, those events will have x1 prime, x2, y1 prime, z1 prime, and t1 prime, and they will also have x2 prime, y2 prime, z2 prime, t2 prime, except that in this reference frame, t1 will be equal to t2. t1 prime will be equal to t2. Now the first thing to do, now let's compute or write down the Laurent transformation between time t prime and time t. So the time t prime is the one recorded in the moving reference frame, and the time t is the one recorded in the K reference frame. So t1 prime is equal to gamma t1 minus v over c squared x1, and t2 prime is equal to gamma t2 minus v over c squared x2. And we have both times are equal. So t1 prime is equal t2 prime because they will be seen simultaneously in the reference frame K prime. So let's write down the equations. This gives easily by simplifying gamma. This will give t1 minus v over c squared x1 is equal to t2 minus v over c squared x2. We know that t1 is equal to 2a over c minus v over c squared, and x1 is a, is equal to t2 is 3a over 2c minus v over c squared, and x2 is 2a. So x2 is 2a. So this is multiplied by 2a. Well, I can get rid of a already. I know that I can get rid of a. And I can also group the v's together. So I will get 2v c squared minus v squared is equal to 3 over 2c minus 2 over c. So 2 over vc squared will give me v over c squared. This will give me 3 minus 4 over 2c. So this means that the velocity will be minus c over 2. So the reference frame will be moving K prime, the reference frame K prime will be moving with the velocity of minus c over 2, or minus half of the speed of light with respect to the first reference frame. So for the two reference frame, or for the two event t1, t2 to be seen simultaneously in K prime. Okay, so for that I will stop, and in the next video I will be covering more on relativistic and momentum, relativistic kinetic energy, and other quantities.